Hello, welcome back to lecture number 11. This time we are talking about deep learning. So essentially we are going to continue what we started last time with neural networks and move on towards the more modern deep learning architectures. So remember, last time we started defining a single artificial neuron. The perceptron goes back to the 1950s. And you've seen that it's a very simple mathematical model. Now, basically, we have inputs. Inputs are connected with weights. We have one special unit that's always one, the bias, also connected with a weight. We compute a weighted sum. The weighted sum goes into an activation function, and the activation function gives an output. We've seen that there are various limits to just having a single neuron, but we can make more capable classifiers by combining multiple of these neurons together. So that's the idea of a neural network. Again, we have an input vector, but now the input is connected to multiple neurons. And you can see the classical three-layer architecture here. We have an input layer with the input vector connecting to a hidden layer, and then the hidden layer connecting to the output layer. And we talked about how to train this kind of network, the backpropagation algorithm, where you feed forward the input. Then you look at the difference between the expected output from the training data versus the output that the network computed. And then you get the error, and then you can propagate the error backwards and update the weights. And over time, the network hopefully gets better in learning the input data. We've seen one application also last time, the computation of word embeddings with the word-to-vec idea. The network architecture here, again, is a three-layer network. And this kind of network is also called an autoencoder because it has the same output layer as the input layer. We've seen that we are updating the weights just like before using the backpropagation algorithm. And another feature was that we weren't actually interested in the network as such. Only thing we were interested were the hidden weights, which became our word vectors. Now, in the big scheme of things, you all know about deep learning. That is the hot topic in AI. But again, the idea of these artificial neurons goes back to the 1950s with the perceptron, and backpropagation was also known 1960s, but it wasn't really possible to use them because of the high computational demand. So in the second big phase of artificial intelligence, where people made use of machine learning, these neural networks became again more popular. And this is where people use these three-layer architectures that I've shown you. In theory, people already knew that if you add more layers, you can learn more complex representations. But again, it wasn't really possible with the amount of data and the processing power at the time to train these bigger networks. So neural networks at that time in the 80s, 90s, mostly meant these classical three-layer architectures that we've seen here. What's the difference between neural networks and deep learning? Well, deep learning, again, is nothing really different from neural networks. Remember, I also told you that AI went through a couple of phases with hype and AI winters, where first AI overpromised on what it was able to do, and then people became disillusioned and sort of gave up on AI for a while until the next hype phase began. So now we are essentially in the third hype phase of AI. Now there was a first AI winter in the 1960s, 70s. Then machine learning was again another hype phase, including neural networks. And again, people became disillusioned with AI failing to deliver on more complex real-world problems. So this includes both expert systems at the time and neural networks. So now we are in the sort of the next hype wave of AI. Deep learning are still neural networks. They are just called deep learning. Well, first because it sounds cooler. People had this disillusionment with neural networks, so it's sort of a rebranding. It's a better marketing term. Instead of reminding people of what they failed to deliver in the 90s, now calling it deep learning makes it sound like it's something completely different. But essentially, we are still talking about neural networks. You'll see that one of the main differences is that we can now train bigger networks, not just 3 layers, input, hidden output. We'll have a lot more layers in there, and these networks are able to do to perform a lot better than the old networks at the time. So today we'll see an example on what we can do with these new deep learning networks. We'll see one architecture called the Convolutional Neural Network, CNN, and apply it to both image and text processing. By the way, these word vectors here, they are also fall into the domain of deep learning. So you'll see word embeddings mentioned in the context of deep learning, even though it's just a 3-layer architecture, so not different really from before. But what makes it different is the sheer scale of processing that you do. Now, I mentioned one set of word vectors people use has been trained on Google's 100 billion word news corpus. And that amount of processing just wouldn't have been possible in the 1990s. So these word embeddings, word2vec, are also attributed to deep learning, even though the network architecture itself is quite traditional. So let's do something. Let's look at image classification, a classical problem, a supervised training task. We show images and we want the system to be able to recognize what's on the image. There is a standard dataset, the CFR10 dataset, which, as the 10 suggests, has 10 different classes: airplane, automobile, bird, cat, and so on. And it's a classification task. So given an image, we want to know what's on there. Is it a cat? Is it a bird? Is it a car? So in this data set that there are lots of people use for experiments and comparison, there are 60,000 images and they are all quite small. So what you see here is the original size of the image. It's a 32 by 32 pixel image. So this is not a preview of some sort. This is the original image size. So it's quite hard with these small images to identify what's on there, even for a human. For some of them, it's quite clear what you see. Now you can see that there is a horse or a boat, but for others, it's a bit harder. Like, what is this even supposed to be? So let's try to classify this automatically with a neural network. And we're going to use, again, like last time, the TensorFlow. And I explained that Keras, since, again, last year or so, is using TensorFlow only as the backend for processing. So the API we're using to TensorFlow is the Keras API. Similar to scikit-learn, you can just load the dataset with a helper function here. So that's shown here. CFR10 is the dataset that we want. We make a train test split. We have 10 classes in that dataset. And yeah, we just load the dataset into the variables here, X and Y, train and test. So we're using a train test split of 50,000 images for training, and then 10,000 images for testing, for evaluating our classifier. So the X train, the array that we are loading here, has the shape 50,000, 32, 32, 3. 50,000 because it's 50,000 images. Each image has 32 by 32 pixels, and it also has 3 different channels. So you can see those are color images. So each image has 32 by 32 by 3 channels, where the channels are the RGB values, the red, green, blue. And the values are between 0 and 255. And for training, we are normalizing them to 0, 1. So this here is called a 4-dimensional tensor. And I'll explain in a minute what a tensor is exactly. So just as an example, if you access the element here in X train 54, 12, 13, 1, you get a certain value, 0.3686. So this is image number 54, looking at the pixel at the coordinates 12, 13, and looking at the green channel. Red is 0, green is 1. And the value of that channel is the normalized value from 0 to 255, which is 0.36. Now you've heard of TensorFlow, and you might wonder, what is a tensor exactly? Well, this is just an n-dimensional array where n is bigger than 2. So a scalar is essentially a single value. We've worked with vectors a lot, so 2-dimensional sets of values. You know what a matrix is, so this is multi-dimensional array, and then a tensor is an n-dimensional array where n is bigger than 2. So let's try to build a neural network. What we're going to use is the images on the input, obviously, and then we have to feed each single pixel of the input into an input layer. So the input is 2-dimensional, but our input layer here is 1-dimensional. So what we have to do is we have to flatten the image. So basically the first row of pixels, then the second row of pixels, and so on. So we get one long input vector for this image. Then we feed this into the next layer. So the overall architecture is we have 2 hidden layers. So it's not a completely classical architecture because we have 2 hidden layers, but still not really full deep learning either. So in there, we have our hidden layers, and we're using an activation function that I'll show you later called ReLU. Last time we used the sigmoid activation function for the classical backpropagation, and I'll show you another activation function that we'll use later on here. And then for the output layer, we have exactly 10 classes. We have 10 different image categories. So we have 10 neurons in the output layer, and we're using the softmax activation function that we've also looked at last time. So this gives us a value between 0 and 1, like a probability distribution for the output classes. Then it will tell us with the highest probability what kind of class we see in the input. Okay, so now we have to encode this into Keras. So we have to import a number of helper functions for building neural network layers and classifiers. So our input layer here is 32 by 32 by 3. Then we use a layer called flatten, which we apply on the hidden layer. So this just transforms our 2-dimensional images into a 1-dimensional vector. Then we have 2 hidden layers, one with 200 neurons and one with 150 neurons. And then we have the output layer where we use num classes. This is what we defined a bit earlier here. Remember, 10 classes from the training data. And we're using the softmax activation function in the output layer. And here we're using the ReLU activation function. And then we are building the model from input to output layer. So what is the ReLU activation function? It looks like this. It's the rectified linear unit activation function. So between 0 and -infinity, the output is always 0. And for values bigger than 0, it's the identity function. So input 1 gives output 1, input 2 gives output 2, and so on. So y equals x. So I'm not really going to talk about all of these different kind of activation functions. There are a number of variations on ReLU. If you want to read a bit more, there is a good explanation here. For now, just accept that this is the activation function that we're going to use now for the network training. Now we have to build the classifier that gives us the model. So we need the optimizer that computes the loss at the output and then does the back propagation for the values. So in the different toolkits, there are different optimizers, and Adam is one of the most widely used ones. So again, here in this course, we're not really going into the theory of the different optimization strategies. We're just going to use one of them. We talked about the learning rate last time. So we are using the Adam optimizer with a learning rate of 0.0005. We have to define the loss function, the optimizer we just defined here, and the accuracy metric. Now, a nice thing with Keras is that once you define the network, you can print out the architecture. So it will tell you layer by layer what you just defined in the program. So you can double check that what you get is really what you wanted to have. This is the conceptual image. So it's like the design of the network, what you want to achieve. Then you implement the design using Keras. And once you're done, you can compile it and you can print out the architecture here. So you can see the input layer. We are flattening the input. We have two dense layers. Dense just means that it's fully connected. So if you look at the network here, meaning every node here is connected with every node here. So that's a dense layer. And yeah, the last layer is the output layer. So now you can see how many weights you have in there. Yeah, remember we did it by hand last time for a single neuron, for a perceptron. You updated the weights. So now we have all the weights here and here and here, and it will show you how many there are actually. So this is just a conversion, not really a weight, but then we have these three sets of weights here. It's getting smaller between the layers, but still you have 614,000 here, then 30,000 and 1,500, which gives us in total weights we have to learn, parameters that are changed during training of 646,260 weights. And on the worksheet, you can now do the calculation for all of them for one set of training data. Now, did any believe that? You come back in 2 years. So yeah, you can see that there is a lot of calculations to be done, even for a simple network like this. So doing the actual training, very similar to scikit-learn. Yeah, you call fit with the parameters that we have, the training data, the expected output, batch size of 32, meaning we update the weights every 32 images. We run 10 epochs, and in between we are shuffling the input images so they don't always appear in the same order, which again helps with the weight updates, that you don't have cases where when they always appear in the same order, that the weight updates sort of cancel each other out. Now, when you run it through these 10 epochs, you see the output. So it is going to take a bit. Here, you'll see it goes through the training data. It doesn't take that long. This is not trained on any fast system. It's did it on the standard desktop computer. So one epoch took 13 seconds. And you can see the accuracy of the network on the training data, sorry, on the testing data. So you can download the whole configuration or just copy and paste it from here and try it out yourself. For this, you don't need any fancy hardware. You don't need any GPUs or anything. You can easily train this on a standard desktop or laptop computer. And now, after training it for 10 epochs, we have an accuracy of, well, not quite 50% on the testing data. So meaning it gets every second image right on the training data. You might wonder, okay, can we get better if we continue training, like for 100 epochs? And then you see there's almost no change here. Slightly better, but this can just be an accident because remember, the weights are initialized randomly every time, so you get slightly different results. Now, maybe we have to train even longer. Let it train for 1000 epochs. And then if you look through this training here, this is going to take a bit longer, obviously. You see that the accuracy on the on the training data goes up to 89%, whereas here we got up to 51%. But now if you check it on the testing data, it's suddenly went down. Before we had 49, 50%. And now, even though it went up on the training data, the performance on the testing data suddenly got worse. So if you remember our lecture on machine learning, you should know what exactly happened here. And I hope you're thinking of what I'm thinking of. So let's print out some of the results that we achieve. So we can write a little helper function that takes the model and randomly picks 10 images and just prints out the image together with the classification, both the classification that is predicted by the network and the actual classification that was in the data. So we are translating the index into the array, the value from 0 to 10 into a label that we can read. And if you run this, it will show you the output for 10 images it picked at random from the testing data. So you can see here, this one is okay. It predicted a horse and it really is a horse, but here it predicted an airplane and it's not an airplane, it's an automobile. This one here, on the other hand, it got right, predicted automobile and it actually is automobile. So for these 10 randomly picked samples, how well did it do? This one is wrong, one correct, wrong, 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 correct, correct. So if I didn't make a mistake, it got, for this sample set, 3 out of 10 correct. A bit less than what you would expect with the 50%, but again, these are picked at random. So on the one hand, it's kind of impressive that on this little thing, it's able to recognize a ship, but on the other hand, yeah, it still makes a lot of mistakes. So here, it's time for a meme. You all know this one. This is the artificial intelligence version of this classical meme. So let's see how we can do better in the next part of the lecture, where I'll tell you how to do the same thing with a deep learning network called a convolutional neural network. See you then.